Good day everyone and welcome to this lectures on physico-chemical processes for wastewater treatment. And in the previous lectures we studied regarding some of the treatment operations which are there, like flow equalization, then we studied aeration in lot of detail. Further we studied coagulation and flocculation in the previous 4 lectures in detail, and we came across that coagulants can help in the bigger floc formation or denser floc formation, which ultimately settle down easily as compared to if we do not use any coagulants. So, they will not settle down. So, once we have reached a condition where lot of solids can settle down, it is very essential that we determine what should be the size of the settling unit or sedimentation unit. So, we will study these aspects in detail now onwards in a few lectures starting from today. And so, like objective of the coagulation and flocculation process was to enhance the size of the particles, so that they will settle in a reasonable period of time. So, once that objective has been reached, so we have to see that we are able to remove most of the settleable solids which are there in the water, either by gravitational settling in a sedimentation basin. So, that is one of the first objectives which is there for settling. Now, these basins may are also called as clarifier or settling tank, etc. So, that is there. So, we most often use gravitational settling. There is a possibility of using some centrifugation or otherwise, but most often it is only gravitational settling that we use in the water treatment. Before starting the design of the system and other things, we should understand the theory behind the sedimentation first. So, today we will be only concentrating on the different types of theories and some of the basics of sedimentation. The settling properties of particles, if they settle down, that can be the overall settling properties can be classified into 4 different groups. So, first thing is called discrete particle settling. That means the particles are like individual particles. Then we have flocculent settling, where some particles are coming together and they are settling down. Then we have hindered settling and compression settling. So, we will study all these things in detail. In actual settling tanks, it is not uncommon to see all these type of settling happening in sequence. So, this is also possible, and individually also they are possible to see all these things. So, we will continue with the same. So, we will study these different types of settlings little bit, and then further we will study in detail these settling behaviors. So, in the discrete particle settling, it is only applicable for very low concentration solids. So, very individual particles are there and they are settling down. So, they settle down as individual entities only, and there is virtually no interaction among the particles, and so this is the discrete particle settling. Now, in the flocculent settling, this is applicable for dilute suspensions of particles that may flocculate or coalesce together. So, this is possible. So, by flocculation the particle size actually increases and the terminal velocity also increases as compared to in the discrete particle settling case. Now, settling can be increased by addition of some other agents such as polymers that we have studied in the previous case. So, it is possible, and that will come under the flocculent settling case. Now, there is third settling which is called as hindered settling. In the hindered settling, generally it is used for suspension, where they are settling at the intermediate rate, and in this case the particles are such close together that the interparticle force due to one hinder the settling of another particle. So, it is possible at that case the particles remains in a fixed position with respect to each other. So, because the settling is being hindered by one another, it is possible that whole bunch is settling down. So, they are in a fixed position with respect to each other, and particles settle down as a whole. So, this is called hindered settling, and then we have lastly the compression settling. So, case in which the particles are in such very high concentration that whole structure is formed. So, compression takes place due to the weight of the whole mass, which continuously increases. So, the structure volume may become less, but the mass will go on increasing. So, this is there, and a clear water will be formed above the compression zone. So, these are the 4 different zones of settling. So, and it is possible to observe all these 4 zones within a settling tank also. So, that is also possible. Now, what we will do is that we will try to understand each of these things, all the 4 cases in further detail. So, today we will be only concentrating on discrete particle settling. So, discrete particle settling is characterized by particles that settle discretely, that means they are not affected by each other, and they will settle down after some time with a constant settling velocity, which is also called as the terminal velocity. Now, since in the discrete particle settling each of the particles behave as individual particles and they do not flocculate. So, there are less chances of observation, but sand and grit are common example, a mixture of abrasive particles that may include sand, broken glass, etc. So, they may settle down as individual particle, and this case is possible in pre-sedimentation unit, like for suppose we want to remove the sand beforehand going for coagulation, etc. So, there this is possible. Now, we will go further with the particle settling theory, that how to find out the terminal velocity of any particle having a particular diameter and having a particular density, and which is settling in a fluid which is having a particular density. So, there are few considerations, that what is the density of the particle, what is the density of the fluid, okay, and what is the particle size that we are considering. So, these are very important parameters that affect the particle settling. So, when particles actually settle discretely, the particle settling velocity can be calculated, and the basin design is based upon this particle settling velocity, and we always design any basin based upon a specific size particle. So, we target that okay, we want to remove all particles up to this size, maybe below that size they may be carried over, but we always decide the specific size which we are targeting for removal. So, the theory can be further be elaborated and we are going to discuss. So, suppose there is a particle like here and it is settling down. So, and it is like it is going downwards in the, so its acceleration is towards downward. So, this is the force which is there, and because of which it is going down, and that force may be the gravitational force. So, generally we will be considering only gravitational force. It is possible that the centrifugal force may also be applied some cases, but we are only considering gravitational force. So, net acceleration in the downward direction will be dependent upon the net, the force by which it is moving downwards, and when the particle is moving downwards, it will be actually be hindered by 2 forces which will be acting in the opposite direction, and one will be the drag force and another will be the buoyancy force. So, these drag force and buoyancy force, they will act opposite to the movement, because the particle is settling down. So, certainly buoyancy force only will be upwards, and drag force is always opposite to the direction of the movement. So, we have 2 forces. So, net we have this external force or gravitational force minus the drag force and the buoyancy force. Now, going further, we will elaborate it further. M is the mass of the particle and u is the settling velocity of the particle in the fluid. So, this is the m into a, this is the acceleration, net acceleration which is there. Now, further expanding it, if F is the drag force and Fb is the buoyancy force, so they can be calculated using this equation. So, this is well known, and drag force is can be calculated using this equation, where AP is the Fd, Cd is called the drag coefficient, and rho f is the fluid density, rho p is the density of the particle which will be used here in the buoyancy force, and AP is the projected area of the particle, okay, assuming it to be the it may possible to assume it to be spherical. So, and m is the mass of the particle. So, drag force can be calculated from here, u is the terminal velocity. Similarly, or the velocity of the particle, buoyancy force is F m into A, and where we like it is the ratio of fluid density to particle density. So, we can see here. So, this is very common buoyancy force, we know very well. So, we now substitute these things in the first equation. So, and AP here in this case the projected area, if we are assuming the particle to be having a spherical particle with diameter dp. So, in this case AP becomes equal to pi dp square by 4, and the mass of the particle is like particle density into volume. So, this volume has been multiplied together. So, we have this. Now, for particles settling with terminal velocity, if suppose the particle is settling at a particular terminal velocity which will not increase further. So, under that condition the rate of change of the velocity will be equal to 0, and under the gravitational force the actual AE value is always equal to g. So, if we substitute all these 4 conditions, the equation of drag force, equation of buoyancy force, then replace the AP value, the projected area assuming the particle to be spherical. Similarly, mass also we can find out particle to be spherical. So, if we do this, we can calculate the terminal velocity. So, terminal velocity can be calculated without replacement of AP and CD. So, we can calculate like this, but if we assume the particle to be spherical, then we can substitute the value of AP in this particular equation, and the equation will become like this. So, this is the terminal velocity as calculated by Newton's method. So, this is the terminal velocity which is given. Now, in this case the drag coefficient which is there, this particular thing is very important, and drag coefficient actually varies depending upon various parameters, and variation of drag coefficient is very important, and it has been shown in classical fluid dynamics, and so we study in detail. So, you will be referred to any of these source also you can refer. So, you can understand further. So, drag coefficient behavior is given like this, and for different types of systems. So, we have 3 zones, one is called Stokes law region, another is called transition region, and another is Newtonian region. So, Newtonian region where CD is a constant value. So, it is becoming virtually constant to a particular value. Similarly, in the first case it is only decreasing at a linear rate, but in between it is changing continuously. So, we have 3 zones. So, for 3 zones we have different equations which can be used for finding out the value of drag coefficient. So, these are given like this. In the laminar Stokes law region, it is also called as a laminar region. So, in this case the CD is given by 24 by RE, where RE is the Reynolds number, and which is defined as rho f into ut terminal velocity into dp the diameter of the particle divided by the viscosity of the fluid. So, that is there, and here in this case the Reynolds number is in the range of 0.01 to 0.1. Some little variations are also reported, sometimes it is used up to 1 also. So, it is possible. Now, if we substitute the CD by 24 by RE and further where Re is equal to rho f ut dp by nu f. So, the original ut equation which is here. So, here we are what we are doing is that we are substituting by 24 by Re, and Re is further being replaced by this term. So, if you solve it, we have ut here Re in the Re also, the Reynolds number. So, and if you solve it, this will be the final equation which will be there for the Reynolds number. So, with respect to Stokes law region. So, if the Reynolds number is only in this range, we can directly apply this particular equation for finding out the terminal velocity of a discrete particle. Now, if suppose the region is not this, it is in the transition zone. So, in the transition zone, different types of equations have been given. So, the equation is this transition zone is valid from 0.1 to 1000 Reynolds number range, and this type of equation has been reported like 18.5 divided by Reynolds number raised to 0.6. Similarly, this type of expressions have been also been reported. There are numerous other types of expressions also reported depending upon the type of particle, type of fluid, etc. So, these are dependent upon them. Then finally, the turbulent zone. For the turbulent zone where the Reynolds number varies from 500 to 2 lakh. So, under this condition the CD is assumed to be independent of Re and it is constant like 0.44. So, there is a fixed value of CD. So, that is why this equation is called as Newton range, and the first original expression if CD is constant here, then it may be called as Newton's method also. So, Newton's method, Stokes region, and then there is a transition region. So, these are there, and this the dependence of CD, the drag coefficient with respect to Reynolds number, can be expressed by this particular equation which is given here. So, we can see here that for Stokes law region the alpha value is 24 and beta value is 1. So, we have the expression like 24 by Re, which was the first expression. Now, if we substitute this to be 18.5 and beta value to be 0.6, we get this particular equation for transition zone, and similarly for third the beta value is 0 and the alpha value is 0.44. So, this way we can have a common equation also, but this is how we can represent the dependence of drag coefficient with respect to Reynolds number. So, now suppose we have to find out the terminal velocity of non-spherical particles. So, Reynolds number is changed a little. This is given by incorporating the shape factor, and the terminal velocity changes by this. So, this is there, and this is the expression for this shape factor which is used and later on. So, we will solve some problem. Now, in this particular expression or any of these expressions, so what we see is that in this case we have to find out the terminal velocity. Now, we have to apply the equation as such that we should know the Reynolds number range. So, for each different Reynolds number range we have different expression, and the Reynolds number itself can be found out only when we have the velocity. So, there is two things, ut is a function we can find out by using this expression, but it is dependent upon the Reynolds number, okay. And Reynolds number itself is a function of ut. So, that means there we have to iterate if we have to find out the velocity. So, suppose any condition is given, so first we have to assume that okay, suppose this condition lies in the Stokes law region. So, we apply the equation for Stokes law region. Once the velocity is known, we find out Reynolds number, we cross check whether actually it is in the Stokes law region or not. So, we iterate between these to solve the problem. So, this is given by this numeric which is given here. A sand particle has an average diameter of 1 millimeter and a shape factor of 0.9 and a specific gravity of 2.1. determine the terminal velocity of the particle settling in water at 20 degree centigrade. Kinematic viscosity of the water has been given, specific gravity has been given to be 1. The drag coefficient in the transition zone can be calculated by this expression, it is given. Okay. Now, we have kinematic viscosity which is given by this. So, we have nu f by rho f is equal to this. So, this value is already given. So, kinematic viscosity is given. So, we can find out nu f also. So, this is multiplied by the density. So, specific gravity is already 1. So, we can find out this. Now, settling velocity, we can first what we are doing, that we are assuming that okay, Stokes law reason is valid. So, if this is valid, so we find out the velocity using this. So, since all the parameters are known and specific gravity of particle is 2.1 and shape factor is also given. So, we can find out the terminal velocity, we can see here. So, it is 0.597 meter per second. So, once the terminal velocity is there, we should cross check whether actually it is in Stokes law region or not. So, we go further and find out the Reynolds number. The Reynolds number is like 536.32 and which is beyond what is given here. So, for Stokes law region, the Reynolds number should be at most 1 or it should be actually less than 0.1, but it is beyond 0.1. So, that means whatever we assumed, it is not correct and Newton's law should not be used for finding out the velocity in the transition zone. So, initial assumption which is given is not valid. So, what we do is that, so we have to adopt the iterative procedure. Now, what we do is that since Reynolds number is known, now we find out the value of drag coefficient. So, CD is known. So, this CD is found. Now, we put in the terminal velocity and we find out the terminal velocity, and from here we have to find out the Reynolds number again and again put in this CD expression to find out. So, this way we have to iterate. So, now this iterative procedure will be like first we find out the UT, from UT we find out the Reynolds number, from Reynolds number we find out the drag coefficient, and once drag coefficient is known, we find out the UT value. So, when we cross check what is the difference which is there. So, if the difference is not much, we can stop there. Okay. So, this UT is found, this UT is put here, again the procedure is repeated, we find out Reynolds number, drag coefficient, again UT is found, we found significant difference is there and we cannot solve the terminal velocity. We can get the terminal velocity under those conditions when the difference is virtually 0. So, we always look for this condition where we see that this was the terminal velocity, and from this if we find the Reynolds number, further find the drag coefficient, and using the drag coefficient we find the terminal velocity and both are same. So, these are the final condition which are there and we can assume that final settling velocity or terminal velocity to be 0.1419. So, this is a iterative procedure which is complicated. So, there is a non-iterative method for determining terminal velocity which is given in few books. So, that also we can refer to. So, determining the settling velocity of a particle of known diameter by the previous method requires a lot of trial and error. Since the particle Reynolds number is unknown initially and one cannot select the proper equation which can be used for drag force. So, that becomes a difficult situation. So, a non-iterative method actually was developed which requires some rearrangement of the drag force equations and solution with respect to settling velocity. So, it can be given by this method. So, in this method what we do is that this is how this non-iterative method has been developed. So, what we do is that we find out if we multiply the terminal velocity expression, like this is the UT expression which was there 18 nu f, if you remember, this is the expression with respect to, and this is multiplied together by dp rho by nu, and this is for with respect to fluid. Okay. So, this is for fluid, we are multiplying. So, wherever P is not written, that is for fluid. Now, if we multiply it by this, so this expression will be obtained, dP will be here, okay. F will be there, the F or F is same as drag coefficient, sorry. So, this is there, and then we have rho P and rho of the fluid and nu F of the fluid. So, if we multiply together, this expression can be obtained, which is the K that we take. Now, if we use this expression and we cross check with respect to Stokes law region. So, suppose Stokes law region is considered in some of the books, it is considered up to 2 also, in some of the books it is considered up to 0.1. So, if the Stokes law region is considered up to 2, which is there in many books, so the original expression can be written as the Reynolds number is equal to k cube divided by 18. So, we can easily write this expression. So, earlier remember the CD value was given to be for this particular Stokes law region 24 by RE, and this expression can be changed. So, we can write for RE and this expression can be changed with respect to this. So, CD in place of CD will have F, and overall this expression can be obtained. And once this expression, similarly for turbulent region, this expression can be obtained. So, sorry, for anything beyond 500. So, for turbulent region where the CD value was constant, CD value was given to be 0.44. So, for this case also we can find out. So, this will be the expression, and if we actually, since Reynolds number range is known, we can easily convert these things into this form. So, K, if the K determined by this particular equation is found to be less than 3.3, it is Stokes law region, and if it is in this range, it is intermediate or Newton's law region. So, this is there, and what we do is that we find out K here, and K is, this expression is not a function of, this is not a function of ut. So, there is no velocity term. So, that is why we, in this expression there is no ut term. So, K can be found out directly, and once a K can be found out, we can easily know the region in which it lies, and once we know the region directly, we can directly apply that particular expression. So, we can always solve using this particular non-iterative method for determining the terminal velocity. We will now end this lecture. So, we have started with the basics, how to find out the terminal velocity. This expression is very important, and knowing the terminal velocity helps in the design of the unit. So, we will continue with the settling section in the next lecture, so as to understand the settling and sedimentation in detail. Thank you.